Hello everyone. In this presentation I'm going to outline an ambient assisted living architecture whose main role is to relate among each other the patient's needs and a personal care robot and a smart environment. The three architecture performances are in communication by means of brain-computer interface. In these slides, you can see the talk outline. As a first step, it will be provided a general description of the architecture to identify the roles of each performance composing the system. Then it will be presented the brain-computer interface algorithm designed in this context for a specific application. Next, two proof of concept videos will support the description of the navigation and object manipulation routines which are embedded on the robot. A section is thus dedicated to the experimental results, focusing on the BCI and the robot routine performance. Our aim was to design and implement an architecture that should allow a patient, for example with reduced mobility or bedridden, to be always connected with the smart environment. This connection can be realized, for instance, by making the user aware of which are the available foods or drinks in that specific moment. The system should also be able to understand the user needs, as well as to uniquely formalize the requests in a robot or computer understandable way. And finally, of course, the system should be able to automatically satisfy the patient's request without any physical intervention. In this slide, which represent the implemented system, we tried to correlate the architecture performance in a functional structure. The first performance is the patient who he asks for something without any physical interaction with the surrounding. In this framework, to formalize this request, the patient uses a brain-computer interface or BCI. Then the BCI system sends the request to a personal care robot, in this case a humanoid one, that enables a camera streaming back to the patients that in this way can monitor the situation. It is important to highlight that both the brain-computer interface and the robot are always connected with the block that is named as environment. That updates in a real time, for instance, the food and drink availability to the patient. Once the request has been formalized, the robot should autonomously navigate to the needed stuff and thus comes back to the patient, bringing back the requested stuff. Now let's investigating the BCI block. As known, a brain-computer interface is a direct communication pathway between the human brain and an external device. Typically, it follows a general processing chain that is e.g. preprocessing, feature extraction and selection, and finally classification of the intention. In particular, the feature extraction stage is the most critical one because it determines the BCI timing and accuracy. So in this work, we studied this stage, introducing a novel methodology to reach good performance in two choices synchronous BCIs. For the proposed BCI, we chose to monitor as brain activity patterns some cortical reads related to voluntary movements planning. These reads are clinically known as movement-related potentials or MRPs. To emphasize them, we designed a clinical-based protocol in which the user is asked to move slightly the finger of the desired side, right or left, in order to elicit the MRPs, as shown near the label for here. In this application, the proposed BCI exploits 8 electrodes placed along the sensory motor area to recognize the MRPs that are linked to the hand's movement. A specific signal in the cortical area, known as Bari shaft potential, is used to trigger the trial extraction system. So starting from the trigger signal rising edge, the system waits for 200 milliseconds and then extracts EEG data for 1020 milliseconds backward. This EEG data subset is named trial in the following slides. During the offline machine learning stage, the extracted trials are organized in two observation matrices, one for the left-hand movements and one for the right-hand ones. During the real-time classification, any extracted trials are directly redirected to the feature extraction stage by skipping the next observation matrices step. All the trials within the observation matrices for every single channel are averaged, generating a single averaged waveform per each monitored channel. These waveforms undergo a local binary patterning or LBP routine that oversees the extraction of the binary reference matrices. This one. These binary matrices that are shown on the right of the slides provide easily enable information about the typical cortical response to a specific hand movement. More in detail, the used LBP routine allows codifying a double precision or integer EEG signal, which is a unidimensional time series, into a bidimensional binary matrix according to the differential analysis between the two contiguous values of the EEG signal, as per the pseudocode that we have on the right here. Any new trials is then treated by the LBP routine, generating an unlabeled observation local binary pattern, the UOLBP. This matrix must be compared with both the reference masks, the one from the left-hand movements and the one from the right-hand movements. The comparison is done through an XNOR gate planes that verifies the equality of each element, corresponding element, composing these two matrices. It permits to evaluate the degree of similarity between the unlabeled observation and one of the two reference masks. To assess this similarity, an external counter, that is this one, verifies the number of 1 per each row. Since both the comparison build the feature vector, we expect, for example, that an observation from a right-hand movement will have an high number of 1 during the comparison with the reference mask from the right-hand movement, while it will show a low number of 1 during the comparison with the left-hand movement related mask. Finally, the feature vector is sent to a serial supervector machine, which is trained with a linear kernel according to the Steve Gans method. It exploits the unavoidable idle times among the extraction of the various features which compose the vector to implement a time-continuous SVM. In this kind of SVM, the feature vector as well as the supervectors are treated as time-continuous signals. This choice, rather than a classic parallel SVM, reduces the computation time that is related to the classification step. Here a proof of concept of the BCI working principle, in which it is possible to see how during a real-time application, the finger movement is about for the purpose. The video also shows the possibility of formalizing in a very short time a lot of requests, also by using only two choices. Once the formalized request is sent to the robot, it starts navigating in the environment, following some markers that can be seen in the second panel. These markers are properly placed in the surrounding to define a specific path to reach a preset location containing, for instance, foods or drinks. The robot navigation routine exploits data from both camera and 3D sensors to extract the depth map as shown in the third panel. When the robot reaches the preset location, the object should be placed on a surface, in this case a table, in an equally distributed way, allowing the robot a fully automatic scanning procedure. In particular, the robot manipulates the object and then scans them in order to find a match with the patient's request. If a match is found, the robot brings the stuff back to the patient, otherwise it leaves the object and scrolls to the next one. The here shown proof of concept shows an example of the object manipulation and scan procedure. The video demonstrates how at the moment the overall procedure is led by the central marker position, that is this one. Here it is shown, for example, an automatic scanning procedure in which we can see the object. The here proposed BCI has been tested on 4 healthy subjects from our institution. It showed an overall accuracy of 84% over 2 choices. The 4 heat maps on the top right of the slide show the confusion matrices for each analyzed subject, while the area under curve graph on the bottom right refers to the SVM trained only for the subject 2. Moreover, it should be also underlined that the implemented BCI asks for about 221 milliseconds after the finger movement to provide the actuator the predicted result. It demonstrates the method suitability for application that need for fluid and continuous command. Finally, the decision is stored in the PCR memory. The PCR then plans the movement sequence in about 315 milliseconds. Finally, the experimental results on the navigation system showed that on about 192 record movements, only in the 21% of the cases, the PCR movements were not properly completed due to odometry errors. Concerning the grasping system, 39 grasps and manipulation have been collected, and we can conclude that in the 75% of the cases, the grasp were successful or partially successful. Partially successful means that during the scan, the object was not recognized by the embedded image recognition system. In conclusion, we realized an ambient assisted living architecture based on a brain-computer interface which is able to automatically satisfy the patient's needs. The realized MRP-based brain-computer interface provides an accuracy of about 84% with a classification timing of about 221 milliseconds. It allows, if needed, also a fluid robot driving and a very fast formalization of a theoretically infinite number of requests. Another remarkable result from the laboratory experimentation is that the autonomous PCR successfully completed up to the 75% of the request which has been formalized by the user. Thank you for the attention.